We're going to learn about the normal curve and normal distributions. First, what does a normal distribution look like? Do you remember how much you weighed when you were born? I think I weighed around 6 pounds. In this study that was done in 2002, they took 3,226 babies and found the mean weight to be 7.5 pounds and the standard deviation, so that's that typical distance from the mean, to be 1.2 pounds. As I'm looking at this group, I want to decide what is the median. Well, I know that the median is the middlemost data value. So if I take a look at the median, that median is going to be the value that's right here in the middle, which will end up to be that mean of 3.39 kilograms or 7.5 pounds. What's the mode? For this graph, the mode is the one with the highest frequency. The highest frequency is the highest bar. The highest bar is also right in the middle, which lines up with the mean. What does this tell us about this graph? Well, it turns out that the mean and the median and the mode are all the same. What makes a normal curve? Well, we've seen that the mean, the median, and the mode all happen at the peak. We also have this tapering off on either end, which gives us symmetry around the peak. I've got it tapering down on the left and tapering down on the right. This gives us three characteristics of a normal curve and a normal distribution of data. We've got symmetry about that peak. The mean is the same as the median, the same as the mode, all happen at that peak. And our data tapers off evenly at either end. Let's look at some other normal distributions. Here's one. Do you play Monopoly or maybe Settlers of Catan? If you do, you have rolled 2 die before, and you might realize that 7 shows up the most, but 2 and 12, the sum of those 2 die, show up the least. And that's because rolling 2 die is a normal distribution. We've got 7, which is the most frequent occurrence, and it tapers off evenly on the left and on the right. Blood pressure is another example. This one's not a perfect normal distribution, but it's pretty darn close. We can see that we've got a common, most frequent distribution right here around, I don't know, what would that be? Maybe 87 beats per minute, and it tapers off evenly on either side. Heights for men and women are also normally distributed. From this graph, we can estimate the mean height for both men and for women. Looking at that pink graph, the mean height for men looks like it's right around maybe 70 to 71 inches. For women, over here on the blue graph, it looks like it's right around somewhere between 65 and 66 inches. Which distribution has the biggest standard deviation? Standard deviation measures spread of data, that variation of data. So I noticed that men's values spread around, let's see, 56 to about 83, which is a bigger spread than the women's heights. So we would say that the men has the bigger standard deviation for heights. And then finally, number 3, what are the chances that you know a woman who's 6 feet 3 inches tall? If I take a look at my graph for the women's heights, 6 feet 3 would be 75 inches, which is way over here, and that would have a very, very low frequency, nearly 0%. Okay, how'd we do? Around 71 and 65. Men has the largest standard deviation and almost a 0% chance of knowing a woman that is 75 inches tall. The normal curve and predicting percentages. The nice thing about normal distributions is they follow some really common rules. This one is the 68, 95, 99.7% rule. Under a normal distribution, all of our data is included, 100% of the data. If I take a look at this lighter blue region, the lighter blue region, we've got standard scores. These count standard deviations. So the data that consists of those with standard scores between -1 and 1, so values within 1 standard deviation, that constitutes 68% of all of the data. If we stretch out a little bit further, whoops, let me go back here. If we stretch out a little bit further to within 2 standard deviations, that's going to constitute now 95% of all of the data that's represented by this curve. And then finally, adding on that darker blue region within 3 standard deviations, we have nearly all of the data represented at 99.7. Normally distributed data sets, especially ones that have a very, very large amount of data, follow the 68%, 95%, 99.7% rule. Let's take that newborn birth weight graph and answer some questions about it. What percent of the data set is within 6.3 and 8.7 pounds? Well, what does 6.3 and 8.7 represent? 7.5 is my mean. So if I add 1.2 to it, I get 8.7. Subtracting 1.2, my standard deviation gives me 6.3. So this is actually within 1 standard deviation. If I use my 68, 95, 99.7% rule, this should be 68%. Second question, what percent of newborns weigh more than 9.9? 9.9 is at 2 standard deviations. I know that everybody between 2 standard deviations is at 95%. That leaves me with 5% of the data outside of that. If I divide it by 2, 2.5 should give me that value above 2 standard deviations, above 9.9. And then finally, the percent of newborns that weigh less than 7.5. 7.5 is right here in the middle. Remember, 100% of the data values are represented under this curve, so less than 7.5 would be half. Let's see how we did. Look at what I've done. I actually took those weights and I put them against this normal curve with standard scores. Like we mentioned in the earlier slide, 8.7 and 6.3 pounds are 1 standard deviation away. So between 6.3 and 8.7 pounds would be our 68%. 9.9 pounds, that one is 2 standard deviations above. So anybody that's 2 standard deviations away is 95%. So we take 100% and subtract 95. Divide that by 2 because we only want the upper portion, and that leaves me with 2.5%. And then the percent of newborns that weigh less than 7.5, 7.5 is right smack in the middle. So everybody, all of the data to the left of 7.5 would be 50%. We're going to go through a lot of examples using the normal curve in my skill building videos.